Hello everyone, welcome to lecture 4 on digital signal processing. So today's class we are going to see what is quantization of continuous amplitude signal. So what basically your quantization is. So I've used this word in my previous lecture, but I've never, we have not seen what it is actually in terms of theory and in terms of mathematical proof. So in today's class, what I'm going to do is I'm going to tell you what quantization is. So the quantization basically means discretization in amplitude. So when I say it's discretizing your signal in amplitude, so it's like different from what sampling is doing, because sampling is doing your discretization in time. So a sampling and quantization taken together, gives your digital signal. So sampling refers to discretization in time, whereas quantization refers to your discretization in amplitude. So the textbook definition of quantization is the process of converting a discrete time continuous amplitude signal into a digital signal. So which means here what basically we are doing is we are taking your continuous amplitude, your amplitude which is continuous, and means your amplitude can have any values from minus infinity to plus infinity, and those values are now turned into a fixed value which can be fitted inside your computing machines. So why we do this sampling and quantization, it's to convert your analog signal into a digital signal. So when I do both sampling and quantization on any given signal, together I have my digital signal. I call it, when I say it is a digital signal, so it's like vague. People say why it is. So it's just like your signals can now be stored in a computing machine. So what happens is when I say I'm having an 8-bit quantizer, so which means I'm translating all the values into this 8-bit values, and these 8-bit values can be stored in any computer and can be processed. It can be, it can be changed into any form, and it can be stored in any form. So that is basically what it means when I say my quantization is discretization in amplitude. Now let us see what is the mathematical model for quantization. So the mathematical model for quantization, we can represent quantization as an LTI system where my input is x of n and my q is my system function quantization, and xq of n is your quantized values. So since we are talking about altering or changing amplitude for quantization, so that is why we are using this q of x of n. And one of the disadvantage, or what happens when you do quantization is it leads to certain loss of information, because basically even your sampling or quantization is what it is doing is it's approximating your continuous signal into a digital signal. So which means it's not exactly equal, it is an approximation, and whenever you do approximation of different quantities, you definitely tend to lose information. So the same way for quantization also you tend to lose information, and that loss of information is your quantization error, which is given by xq of n. So it is your signal after quantization minus x of n, and which is your signal pre-quantization. So when I take the difference of values between these two, I get eq of n, and that is your quantization error. You can see the example shown here. So your quantization error can be both positive as well as negative, but it cannot go beyond a certain range, which we are going to see in the coming slides. So what are the different stages of quantization? So here I'm going to talk to you about the steps involved in quantization. So we are talking only in terms of the basic quantizer. So we're just getting started. So we don't want to bring in already complex designs, quantizers like non-uniform quantizers, or there are a much advanced quantizer and state-of-the-art quantizers which are like much more complicated than what we are seeing here. But to start with, the basic quantizer must have two main stages. The one is your truncation. The next one is your rounding. So every quantization must have these two. So a truncation is very important because you may have values which needs clipping. So when I say it needs clipping, so I may have a value which is like having 8 decimal places, right? 8 values after my decimal point, and I don't need my 8 values, so I just truncate. I just do truncation and keep only the 2 values after my decimal points. and it can be the same for pre-decimal, but that's going to tend, because if I do the truncation, before your decimal 1000, if I remove 2 zeros, it becomes 10, but that approximation makes your signal lose a lot of information. So what your information was 1000 before, it is now just 10. So the truncation usually happens to the parts on your right side of the decimal place. Good. Next, we see something called as your quantization levels. So what is quantization level? The quantization level is the values allowed in your digital signal. So the rounding, the second stage of your quantization is your rounding. It's your basic rounding, and that rounding happens. So whenever that rounding happens, it has to round to certain values, and these values are called as quantization levels. So for an 8-bit quantizer, I'm talking always 8-bit quantizer because that is one of the most commonly used quantizer in many of the applications. An 8-bit quantizer has levels from 0 to 255, and that is used in most of the machines, like I've written here. And these levels, individual levels, are called as the, here 0, 1, 2, etc. up to 255 levels. And if you take the distance between two successive quantization levels, and that the difference, so in this case it's going to be just 1, 0 to 1 means 1 minus 0, and that is called as your quantizer step size or your quantization resolution. Good. So here your step size is taken as, quantization step size is given as 1, that is for an 8-bit quantizer. And if I define a step size of 0.5, then in my case it's going to be like 0, 0.51, 1.52, and the number of level is going to become 5112. It's going to double. So the now step size is something, it is fixed by the user for our quantizer. So for a uniform quantizer, you have the same step size, whereas for your non-uniform quantizer, you have varying step size. So the next thing we want to see is the mathematical modeling. So we have seen what is quantization, what are the stages of quantization, and what are some of the quantization terminologies like level and resolution and step size. And now we are going to see what is your quantization mathematical model. So in terms of mathematical model, we need two things. That is, we need to know what quantization error is. We need to know what step size is. We need to know a few other things, because the step size tells us where it rounds to. Suppose if my step size is 1, I can say like any value greater than 0.5 is going to be 1 and less than 0.5 is going to be 0. So that helps me fix. So a step size helps to fix your quantization levels and also the quantization function Q. So that is only dependent on your step size. And here we say the range, the quantization range is from minus step size by 2 to plus step size by 2. And also it defines the range of my quantization error. Because whenever I'm having a round off quantizer from 0.5, so less than 0.5 and greater than 0.5, my difference or my range cannot go. Here the quantization range cannot go beyond minus delta by 2. Understood? So whenever the step, so here the level, the difference between the level is 1 or the step is 1, and which means my round off happens at position 0.5. The middle position is 0.5. So that is what my minus delta by 2. I can have a quantization of error up to minus 0.5 or up to plus 0.5. And the example makes this more clear. And now my dynamic range of the signal is given by x max minus x min. So that is your dynamic range of your quantizer. And we also have level range, so which is between two successive level voltages. Okay. So now we have seen few more terminologies. We have seen what step size is, we have seen what quantization error is, and we have seen what is our dynamic range, and we have also seen finally what is the range of your quantization noise, which is minus step size by 2 to plus step size by 2. Now I am telling you that we can represent the step size. So we are going to put more details about the quantizer into your step size. So your step size can have x max minus x min divided by L minus 1, and that is your number of quantization levels. Good. So here L is your number of quantization levels. For an 8-bit quantizer, it's 256, right? It is 2 to the power of 8, so 256 levels. and that is your step size. So we have a new formula for step size which can be computed between. So if you are to design a quantizer based on certain limits, which is your x max, x min, and L, you define you the step size can be calculated from these parameters. Now let's see what our quantization model looks like for a sinusoidal signal. So what we are going to do is we are going to do something. We are going to derive a SQNR. SQNR stands for signal to quantization noise ratio. So we are going to model this and we are going to derive it for a sinusoidal signal. So in order to find your SQNR, you need a signal power and you need a quantization noise power, and both of which we have seen. Your signal power is nothing but the sinusoidal power, and the noise power is nothing but your quantization error, EQ of n power. So finding the power of your EQ of n is what we'll be seeing. So before we get to that, let me draw the schematic. You are illustrating a simple quantization process in your sinusoidal signal. So here your y-axis represents the step size, and the step increment, the quantization level is delta, that is 2 delta minus delta, 3 delta minus 2 delta. The difference between successive sample in the y-axis gives you the quantization level. And now this staircase waveform represents your quantization approximation in amplitude. So as you can see, the approximation is being done in the y-axis. That's why we are not drawing much on the x-axis. So these staircase approximation is your quantization waveform. So as you can see, whenever I'm approximating a sinusoidal signal with quantization, I am definitely losing. The shape is becoming a staircase, or it's more of a square and then a sine at this point, and this approximation is what becomes the quantization error or the quantization noise. And we want to find what is the power of this quantization noise, so that will help us design. So we will later on see how your SQN or your signal to quantization noise ratio can be useful in selecting your quantizer or in designing your quantizer. So now we're going to look at this schematic of a sinusoidal quantizer in more detail. So if I am drawing a cross section of just a single step from the diagram on the left side, so I'm going to have something like this. So where my bold yellow line represents the quantization interval, that is delta. The total quantization interval is delta, and the slant, the slope, is valid from a small time interval of minus delta to plus delta, and this is your value in upper half. So it makes it clear from looking at this dissection zoom. What I can tell you is, if there is a value above the dashed line, that value is going to get rounded to delta top, and if there is a value below the dashed line, that value is going to get rounded to delta down. So these rounding of values, this is basically your round of quantizer. So we can either do truncation first followed by quantization, depending on how many decimal places or precision values we have after decimal places. So here what you see is a rounding happening to delta top or delta down, depending on your position, where that sample position comes inside that grid. So the quantization error, so this is now why we are drawing this is to help us understand how to find the power of your quantization error. So the quantization error is also known as a mean square error, because we are trying to find the power of an error signal, and to find the power we are using the energy expression, which is EQ square. So that's what makes it a mean square error. So now if you say the power of your quantization is equal to 1 by 2 tau integral of minus tau to tau EQ square of t. So that is the equation that I'm going to go with, and this equation I'm obtaining from the diagram that I've just drawn for you. Now I'm just shifting the integrals from minus tau to plus tau to 0 to tau, and I'm going to do that by taking a 2 scalar, and that makes my final equation as 1 by tau integral 0 of tau EQ square t. So these are basic integral substitutions, and after doing this we have that. Now we need to know what is EQ of t. So what is my error signal? So what I'm going to do is how I'm going to represent EQ of t. I'm going back to the diagram. I'm going back to the quantized single step diagram, and here what I'm going to do is I'm going to write the equation for my EQ of t, because the EQ of t takes its place between these two yellow lines. So my EQ of t is the equation of that line. So when I write the equation of that line, that is going to be slope into the signal, and my slope is given by delta by 2 tau, and this is a ramp signal. So my equation for EQ of t is delta by 2 tau into t, and I'm just substituting in this PQ, and then I'm just going to solve that derivative for a limit, right? And then we will see what we get. So from here it becomes very straightforward. So I'll let you watch how this turns out when by doing integration, what we get as your final value. So you are going to get something as del square by 12. Good. So this is the square of your step size divided by 12, and that is your error quantization, right? Mean square error power, or your denominator in SQNR. So we are going to find SQNR, and to find the SQNR we need the signal power to noise power, and the noise power is ready for us. It is del square by 12. We have it now. Now we are moving on to finding your signal power. So so in order to find your signal power, what we are planning to do is we are going to take our before we go to that, we will look at little more about this, because I want to include, like I said, even in the previous case for del we had used an equation x max minus x min divided by L minus 1. That is because we wanted to put more information about the design and more information about the system designs into the step size, and that is why we put it as the dynamic range by number of levels minus 1. Now we are using the another process where we substitute the del with L is equal to 2 to the power of b. So for 8-bit, my quantization level is given by 2 to the power of 8. So we are going to use that here. So the del is being substituted as x max minus x min, which is 2a, 2 into amplitude divided by 2 to the power of b, and this square by 12. Now this incorporates more, because here I know what I can define what is the range of my amplitude, what can be my maximum amplitude, what can be my number of bits. All these things goes into this equation, and this error definition or the error power equation is a much better analysis, provides a much better analysis for your quantizer. Good. So I think that can be our PQ, that can be our finalized PQ for now. Now let's move to the power of the sinusoidal signal, which is not very difficult to find, and it is the power of a cos omega t is a square by 2. So this is well known, this theorem from signals and systems. So we are not going to prove this here. I am just going to write it, and because this is something we ask students to memorize it, and as far as DSP goes, we are not measuring the power, because that comes in the signals and systems. So we are just going to substitute these two values. Now I have a square by 2 for my signal power, and my a square by 3 into 2 to the power of 2b for my noise power. Taking the ratio of these two, what do we have is your final SQNR term. So that's going to come out to be 3 by 2 into 2 to the power of 2b. And now this expresses your SNR in dB or n decibel, right? So this is no, that was in radian. So now in order to express it in dB, what we are planning to do is we are just going to take 10 log 10 of the SQNR. So that is going to be 10 log 10 of 3 by 2 2 to the power of 2b, and that's going to come out to be 1.76 plus 6.02b. So just converting the above XQNR expression to dB, we are getting this. And now you can calculate this with the help of a scientific calculator. So the term we are interested in is 6.02b. So your b is represents a bit, and now you can tell from this equation for every bit your SQNR is going to increase by 6 dB. So that means when your SQNR increases, it means we are having better quality. High SQNR is desired for the better quality of your quantizer, so better performance of your quantizer. So which means every bit is going to increase your SQNR by 6 dB, but at the compromise of more bandwidth, more infrastructure, more computational load, right? There is always trade-off. We have to find a trade-off for the best number of bits that can be used depending on a lot of other parameters, not just the performance. Good. So now that is for quantizers today. We have seen what a quantization is, what is a mathematical model, what is the theory, and what is other things. Now we are going to do, we are going to have numerical. So we are going to close this class with a small numerical. So the numerical is xa of t is equal to 3 cos 2000 pi t plus 5 sin 6000 pi t plus 10 cos 12,000 pi t. So this is an analog signal given to us. Now what we have to do is you have to find your Nyquist rate, you have to find your sampling frequency, then you need to find what is your reconstructed signal going to be. So let's get started with this. So now when I say Nyquist rate, it's very familiar to you by now. We have seen the Nyquist rate is nothing fs sampling frequency, which must be greater than 2 f max for additive signals or for multiple signals. So in this case, we have an additive mixing of 3 signals, f1, f2, f3, individual frequencies, and my Nyquist rate fs is going to be greater than 2 f max. So that frequency is given by so in this case, this is going to be 12 kilohertz. So let's go to the next question, the subpart of next question B. So you need to find for sampling frequency of 5 kilohertz, you're looking at what your DT signal will be, right? So the sampling frequencies, so I'm just going to write it. If we are talking about a folding frequency, so your folding frequency is going to be minus 2.5 or 2.5. So this is your folding frequency. That is not asked in the question, but sometimes they ask question, what is the folding frequency given your sampling frequency? So your sampling frequencies divided by 2 is your folding frequency. So let's do now, what is your discrete time signal going to look like? I'm going to use the sampling formula, which is x of n is equal to xc of n, ts is equal to xc of n by fs, and my dt signal represented by cos 2 pi fn by fs. So this is my cos omega n, and omega is equal to 2 pi fn. So what basically I'm doing here is I'm going to, so I'll write it in a much simpler way. Oh, sorry for this, I have to erase this one. I'll write it in this manner. So xc of n by fs, so I'll just connect these two. The best way to explain this is cos 2 pi fs and n. So I'm clubbing this, your dt signal is cos 2 pi fn, and your continuous signal is xc of n by fs. I'm taking these two and I'm clubbing them, and then I'm writing my sinusoidal signal as f by fn. So now my frequencies are 1, 3, and 6, and my sampling frequency is 5, and that gives you the discrete time signal. Now we are looking at what your reconstructed signal is going to look like. That is your question. So for getting the reconstructed signal, basically we are not looking at other algorithms. So there are many algorithms that can be used for reconstructing signal, like interpolation, upsampling, and etc. Techniques are there, but we are not into oversampling. So we are not doing all those. What basically we are trying to do is we are trying to simplify this expression that we have here. So the dt expression that we have obtained, 3 cos 2 pi 1 by 5, 5 sin 2 pi 3 by 5, and 10 cos 2 by 6 by 5. So we are going to simplify this expression, and we are going to simplify this expression in this manner. So we are going to take what is, so we are going to see what are the components which are having 2 pi. So I am having sine 2 pi, I'm having 1 sine 2 pi in my 3 by 5, and same way I'm having 1 cos 2 pi in my 6 by 5, which is written as 1 minus 2 by 5 and 1 plus 1 by 5. So that is the simplification I'm going to do for reconstruction. Whenever they ask for reconstruction, try to simplify the dt signal that you have with you to the most minimal form as possible. So after I simplify that, I'm going to get this form 13 cos 2 pi into 1 by 5 plus 5 sine 2 by 5 into n. And now I can tell you that this 1 by 5 by n is a signal with frequency 1, since my sampling frequency is 5, and the second component is going to have a frequency of 2 kilohertz. So your original signal is having signal of frequencies of 1k, 3k, and 5k, but your reconstructed signal is having only 1 and 2, which means your aliasing has happened. So there is aliasing happening here. Because why there is an aliasing here? The sampling frequency is taken as 5 kilohertz, and your 2f max is 12 kilohertz, which is so the 5 kilohertz selected is far less than your Nyquist rate of 12 kilohertz, which leads to your aliasing phenomena. Good. So that's for this lecture. We'll see you in next lecture. Thank you.